Hey class. So, unfortunately, the recording did not start appropriately when I recorded this lecture in class. Like I said, I'm kind of new to recording my lectures during class, so there's probably going to be a couple of technical issues that have to be worked out, like this one. But that is why I am recording this again after the fact. And you will not hear some of the engagement from the class that actually happened when we covered this material in class. Regardless, I'm going to basically run through the same material I did in class. However, this first question, you're obviously not here to tell me about what you've heard previously about dynamics. Although you guys did a great job of telling me what your prior conceptions about dynamics were. Some things related to how hard the class is, some things related to kind of syllabus policies that you've heard about. We talked about how there are a couple of different schools of thought in the ways to teach dynamics, and the book and the software that I use most often in this class is different than the book and software that some of the other professors here at FSU teach with. So there is a little bit of a disconnect depending on who was teaching the class in exactly what types of information were emphasized and so forth. So very great discussion that we had about what you've heard about dynamics. And then we started talking about some definitions. So we started talking about how statics refers to objects with zero acceleration. And if an object has zero acceleration, then Newton's second law boils down to the sum of forces equaling zero. And I said that this little symbol here that I've put over top of F denotes that F is a vector quantity. It's not a scalar, but it is in fact a vector, so it has multiple components to it. Okay, and we said that this is different in dynamics. In dynamics, we are assuming that there will not be zero acceleration. And in fact, we will be dealing with non-zero acceleration most of the time. And when there is non-zero acceleration, then Newton's second law becomes the sum of forces is equal to mass times acceleration. And notice here that both forces and accelerations are vector quantities. Mass is not, mass is a scalar, but force and acceleration are. And we talked about how important this equation is for this class. Almost everything that we do in the rest of this class comes back to this sum of forces equals mass times acceleration equation. And this equation is so important that we even have different names for the types of analyses that go with the left-hand side of this equation versus the right-hand side of this equation. Okay, so kinetics, we said, was everything to do with these forces on the left-hand side of the equation. We said this was the kinetics part of the equation. And this right-hand side is what we refer to as the kinematics. Whoops. Part of the equation. And we will define each of those terms below. So kinetics is concerned with the forces that cause movement or acceleration. Whereas kinematics is concerned with the shape and magnitude of movement. And what I mean by that is we're going to talk about how to analyze quantities like position, velocity, and acceleration. Okay. Left-hand side, or the sum of forces, is the kinetics part of the problem. Right-hand side, mass times acceleration, is the kinematics part of the problem. All right, and then we started talking about this idea of space, and we said that space in this class is going to refer to the environment within which objects move. And in the physical world that we occupy, we most often talk about movement in 3 dimensions. We can go left, right, we can go forward, backwards, we can go up, down. Or better yet, we can move in the x direction, the y direction, or the z direction. And so often the way that we visualize a space is by drawing a coordinate axes like I've just done, or a reference frame. Next, we talked about time, and I started talking about how in classical mechanics, time is considered to be absolute, whereas in relative mechanics, so those mechanics that have been described by Einstein's theory of relativity, time does very strange things in that domain. So for this class in particular, time will be considered absolute, and time is experienced the same way between different objects regardless of how those objects are moving. So in other words, what you are used to considering as time, that is the time that we're going to consider in this class. Okay, so time is a scalar variable by which we specify the order of a sequence of events. And for classical mechanics, that's this class, classical mechanics, time is considered absolute as opposed to relative. Okay. Force, we say that the force on an object is the interaction between an object and its environment. And we represent forces with vectors. And we had a little bit of a discussion here about why this definition is important when we consider how we draw a free body diagram. So if a force is the interaction between an object and its environment, when we draw a free body diagram, we want to free that object from its environment, and we replace all of the connections that really truly do exist between that object and the environment. We replace those visual connections with forces representing the force of that interaction. Okay, and we'll do an example, 2 examples actually at the end of this lecture where we draw really good free body diagrams. And we talked about how free body diagrams are crucial to get right, because if you draw the wrong free body diagram in this class, it's almost impossible to get the right or correct answer through the rest of the problem, because it means that you're ignoring some forces that exist but that you kind of ignored. Okay, then we started talking about mass and inertia. It turns out there are 2 different inertias. You can consider mass as an inertia, but there's also what we call the mass moment of inertia. And we had a discussion about how mass is the resistance of a body to linear acceleration, and mass moment of inertia, or I, is the resistance of a body to angular acceleration. Okay, so let's write some notes here and then I'll talk about that again. So mass is a measure of the amount of matter in an object. But this definition isn't super useful to us. I prefer to think of mass as the resistance of a body to linear acceleration. So inertia is the body's resistance to changing its state of motion, that is to say its acceleration, in response to an applied force. Okay, so we said there, the very basic equation in this class is that the sum of forces equals mass times acceleration, and that the sum of moments is equal to I alpha. And I said it's very easy to see here that mass and mass moment of inertia are creating this kind of scaling of the relationship between the force and the resultant movement. So if mass were 1, if we just multiplied a value 1 times acceleration, we would essentially be saying that the sum of forces is equal to acceleration. They are absolutely equal to each other. And so if you think about mass as modifying that relationship by scaling it up or down. Okay. And then here this is talking about linear movement. And this is talking about angular or rotational movement. Okay? These are the two inertias, mass and mass moment of inertia. And mass you should be fairly familiar with. The mass moment of inertia, however, is going to be basically an entire chapter in this class, is how do we find mass moment of inertia, and then of course we will use it thereafter. Oops, I erased too much. There we go. All right, then we started talking about two different types of objects, and we will be dealing with both in this class. And I said a particle is a theoretical type of object that, in fact, does not exist in real life. And the reason that it is just this theoretical object is because it's an object with zero volume. And we know that in real life, there's really nothing at all with zero volume. Everything takes up some amount of space in real life. So this particle is a theoretical object whose mass is concentrated at a single point. And the reason that we think about particles in this class so much is because all of the content that we work with, we're going to start with the simplest version of that theoretical concept that we can, and we're going to build up in complexity. So when we first start looking at a new concept, we're going to apply that concept to particles, and because that particle has no volume and is just a single point mass, some of the math is going to be simpler for applying that theorem to a particle than it would be to apply that theorem to a rigid body. So we will start out thinking about particles, and then we will increase in complexity by then thinking about rigid bodies. So for a rigid body is by definition an object with two properties. One is that the mass of that object is distributed over a region of space. Okay, these are the objects that we're used to seeing in real life, right? Things that have volume, that have mass that is distributed throughout an object, right? And then two, the other really important distinction is that a rigid body is one for which the distance between any 2 points on the body never changes. Okay, so we talked about how if I were to take a point on my pen, 2 points on my pen, and I measured the distance between them, there's nothing that I can do to this pen, no matter how fast it's moving through space, how it's twisting or turning. Those 2 points are never going to move closer or further away from each other if we treat this object as a rigid body. So basically, we're saying that in this class, we are not in any way going to deal with deformable bodies. We're not going to think about any type of object that changes shape over time. So those are later classes. Let's see. I talked about an example of a deformable body that would violate this condition. So I talked about Play-Doh, and I said if I make a ball out of Play-Doh and I choose 2 points on that ball of Play-Doh, if I were to then take that Play-Doh and chuck it at a wall and it hits the wall, it's probably going to squish so that those 2 points come closer together. And that's how we know that Play-Doh is a deformable body, is because those points, the distance between those 2 points changed. And we don't know how to deal with those types of bodies in this class. We will not be covering that information. We will only be dealing with rigid bodies. Okay, so at this point, we have enough vocabulary to start talking about exactly what we're going to cover in this class. I said for every set of theoretical knowledge that we cover, we're going to start out by covering or applying that idea to particles, and then we will apply that idea to rigid bodies. Okay, I actually have this color coding scheme in our syllabus. If you look at our day-to-day schedule, I've highlighted every day's content as being particle kinematics, particle kinetics, particle work energy, or particle impulse momentum, or rigid body kinematics, rigid body kinetics, rigid body work energy, rigid body impulse momentum. Okay, and in fact, this is the order in which we're going to do the information as well. We're going to start out with kinematics, and then we're going to talk kinetics. Okay, so we're going to talk mostly about positions, velocities, and accelerations. And then we're going to start talking about forces and torques and combining that together through that F equals ma equation to define everything about the movement of that object. Okay, and then once we have brought kinematics and kinetics together, we'll move on to work energy methods as well as impulse momentum methods. Okay? All right. Now, I did say that the way that I cover dynamics is not as vector heavy as the way that other professors cover it, but that is not to say that we won't be using vectors extensively in this class. We absolutely will. Like I said, the way that we define forces, the way that we define accelerations, these are vector quantities, so we have to treat them as vectors. All right, and as such, we need to review some vector math just to be absolutely certain that we're all on the same page about how we manipulate vectors. Okay, so let's do some examples based on a vector A and a vector B that I have here. And the first thing that we're going to do is add these two things together. Okay, and the way that we add them is by simply adding up each component. And I will do that, for instance, by saying 4 plus 9. 4 is from vector A, 9 is from vector B, plus 3 minus 2 in the J component. Oh, sorry, these keep their components. Adding and subtracting vectors results in vectors. And then last, for the K component, I have 10 plus 2. I trust that you guys can simplify. And then we talked about multiplying by a scalar, where we just need to distribute this scalar to each component of our vector. So if we want to multiply vector A by 4, I simply need to take that 4 and multiply it by the I component, multiply it by the J component, and multiply it by the K component. Okay, and then we discussed that there are two ways that we can multiply two vectors together. One is called a dot product, and the resultant of a dot product is a scalar. The other is the cross product, and the resultant of a cross product is another vector. Okay, so if we want to find the dot product of A and B, I need to multiply the components of A and B. I will do that for all three of the components, and then I will add up those results. Okay, so this means for our A and B, we have 4 times 9 plus, we lose our I component there. 4 times 9 plus 3 times negative 2 plus 10 times 2. And lastly is the cross product. And the cross product results in another vector. It is probably the most complicated operation that we need to know how to do. And I made it clear that however you work through the mechanics of taking a cross product, I know there are a couple of different ways to memorize how a cross product works, is absolutely fine for this class. I don't care how you do it as long as you get the correct answer. But I will show you the way that I do it, and the way that I will do it in the notes. Okay, so the way that I do it is by writing out this array I, J, K, and then I start with this vector. I lay out vector A, so this will be 4, 3, 10, and then I lay out vector B, which is 9, minus 2, 2. Okay, and then I refer back to this array for each component of my cross product. Now, the resultant cross product is going to have this kind of structure to it. I'm going to have some positive I component, and then I add a negative for the J component, and then I have a positive K component. Okay, so you'll notice I've left a space in here. Each of these spaces, I'm going to do some multiplication of certain subsections of this array that I've drawn. So let's look at what we do for the I component. For the I component, I want to kind of hone in on this part of my array. And what goes over here, I call it doing the forward minus the backward product. So I'm going to take 3 times 2 minus 2 times 10. Okay, so then minus results in a positive. Okay, the next component, I'm going to do the same thing, but I'm going to look at a different part of this array. In fact, I'm going to look at the kind of matrix that forms from these two columns, the outer columns, and again, I'll do forwards minus backwards. I'll do 4 times 2 is 8, minus the backwards product, which is 9 times 10, or 90. And then lastly, I'm going to look specifically at this part and do the same thing. So for the K component, I'll have 4 times minus 2 is minus 8. Forward minus the backwards, so minus 27. Okay, and then you can simplify on your own. Okay, unfortunately, I had to speed through the trig in class. I might actually go ahead and show you my trig trick right now. So you do need to know basically SOHCAHTOA, which says that sine of theta is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse. And tangent theta is equal to opposite over adjacent. Okay, and I've labeled these here on a canonical right triangle. So if we have some theta angle, the side that is adjacent to that theta is your adjacent. The side that it is opposite of your theta is your opposite side. And of course, the hypotenuse is the one that connects those two. Let's see here. So what I really wanted to cover is an example of where the trig gets tricky, and that's going to show up in several different problems that we do together. So I'm going to go ahead and draw the object where the trig particularly gets messy. So let's say we want to consider an object that is resting on an inclined plane. I don't care what that object is. Maybe it's a box, maybe it's a car, maybe it's a bike. I don't care what it is. I'm just going to draw it as a box. Okay. And let's say I want to draw the free body diagram of this box. Well, the box is still going to be tilted up in space, right? That doesn't change the direction that gravity works. Gravity is still going to be going straight down, so the weight or the force due to gravity is going to be straight down. Maybe this box is, maybe there's some friction between this box and the plane, and so maybe we have a friction force that goes parallel to the inclined plane surface, force of friction, and then we absolutely have a normal force that is perpendicular to the plane surface. Okay. The next question that we're going to have to work through together when we do an actual problem together is deciding how you want to orient your axes. Okay, so you're going to have to define what is the x direction and what is the y direction. And we have a couple of choices. Well, actually, you have an infinite number of choices. You can absolutely choose any orientation of x and y that you wish. As long as you use that orientation consistently throughout the problem, it does not matter theoretically. However, there are good choices and bad choices. There are two most obvious choices that you should choose between, and that is you either want to set your axes so that one direction is perfectly up and the other direction is perfectly left and right. So we might have x and y like this. Or you want to use a tilted coordinate system in which we tilt our coordinate system to match the tilt of the inclined plane. And the reason that we use these two options is because we're going to have to resolve our forces into components. And each of these options means that one or more forces will have all of its force along a single component or along a single direction. So for example, let's say we choose a left, right, up, down coordinate system like I've shown here. If I wanted to write W, the weight due to gravity, as a vector, I would say that W as a vector is equal to all of W in the minus J component, right? Because it goes straight down in the exact same direction as y, except that it points down instead of up. All right. The problem is that now our vector Fn, if I want to write Fn as a vector, part of Fn is going to go in the x direction and part of it is going to go in the y direction. And I have to very carefully use trigonometry to figure out exactly how much goes in each component direction. Okay, so that means that writing Fn and Ff as vectors is going to need to use trig. And that trig is just going to be kind of nasty. Okay, so these are what's going to happen if I choose the straight up and down, directly left and right coordinate axes. But let's see what happens if I choose the other way. I've got my free body diagram here. It's nice and tilted. F, N, W. If I choose a tilted coordinate system, like this, and I say, we're going to choose X, my X direction, such that it is collinear with my force of friction, that means that when I go to write the force of friction as a vector, I can say, well, all of the friction force goes in the I hat direction. That's easy enough, right? It's collinear with the x-axis, and it even goes to the right, so it's positive. Similarly, for my F normal, Fn, all of Fn goes in the positive j hat direction. All of it goes in the j hat direction. But now W, or the weight due to gravity, needs to be split up among x and y. Okay, so W is going to have some I hat component and some j hat component, and we're going to have to use trig to figure it out. So if I make this choice up above, I have to do trig for two separate vectors. Whereas if I choose this choice down here, I only have to do trig for one vector. Okay, so for this particular case, this is the better option. For this particular free body diagram, a tilted coordinate axis is the better choice, because I only have to use trig to resolve one vector. Okay, now let's go ahead and figure out how to resolve W into the I hat and j hat component. So here is my trig trick. My trig trick is that you want to draw your trig problem somewhere else, not on your free body diagram. And to do so, you're going to draw both axes. You're going to draw the axis that aligns with W, and the axes that are the tilted coordinate system that you want to use. Okay, so let me just do this, maybe to clarify. So let's say my weight due to gravity is aligned with this non-tilted coordinate system, flat x and directly up y, and I can draw my weight vector here. It goes perfectly in the downward y hat direction. But I am also going to draw my tilted coordinate system. Now this tilted coordinate system says that my x is tilted up and to the right. So we'll call maybe this x primed, and it extends down and to the left, which means that my y hat direction, or my y primed, is going to be like this. Okay. Now, I need to know the angle between these two coordinate systems in order for me to do the trig. And the way that I know the angle is I want to look at all of the wedges created by drawing these two coordinate systems right on top of each other. And I want to find the wedge that looks the same, basically in shape, as the inclined plane that this box is sitting on. So, for example, for what we're looking at here, our inclined plane is horizontal and then opens up from left to right. The wedge that looks like that is this one. Horizontal on the bottom, opens up left to right. That means that this angle is the angle of the inclined plane, which I believe I didn't actually give. Let's call this 30 degrees. Maybe we're at a 30-degree incline. That goes right here, okay? Now, the other thing to keep in mind is that by the nature of the fact that these two coordinate systems are, like the x component is perpendicular to the y component, that means that every other wedge is that same 30 degrees. Every other wedge. Okay? All right, So we have this nifty picture. Now, how do we do the trig problem? Well, we have this W that aligns with our regular X and Y, but we want to figure out how much of it goes in the X prime direction and how much of it goes in the Y prime direction. And so to do that, I'm going to hone in on this part of my drawing. I know now that this angle is 30 degrees. And I'm going to look at this as the right triangle that I'm going to use for my trig. Whoops. This is the right triangle. Nope, that's not right. Sorry. I drew the horizontal part wrong. The right triangle, I need this portion to be parallel with my X primed. And so this is the right triangle that I'm going to use for my trig. Right here. Right here. Okay. So basically what we're saying is that some of the purple vector goes in the negative X prime direction, and some of it goes in the negative Y prime direction. That means that I can write W as equal to, let's see, W minus W sine of 30 I hat. I'm looking specifically at trying to define this vector here. This vector here is opposite the 30 degrees. So honestly, we could say sine of 30 is equal to the quantity I'm concerned with over the hypotenuse, where the hypotenuse is just the amplitude of that W vector. So we'll just call that W. That's like the full mass times acceleration due to gravity. Okay, so this is the I hat component, and then we're going to look at this component here that goes down in the Y direction. So this will be minus W cosine 30. In the J hat direction. And it's minus because it is pointing the opposite direction as Y primed. Y prime points up, but the component that we're looking at that forms part of our W vector, it points down. So it is in the negative J hat direction. Okay, so this is how I get the trig correct. It's just about the only way that I've found to consistently get the trig correct is to draw my trig problem. Draw the trig problem somewhere else other than my free body diagram, and do it by drawing both of the coordinate axes that you're concerned with. So both the tilted and the non-tilted axes. And you use that picture to try to figure out which angle is which, so that you can then identify the right triangle that you used for the trigonometry problem. Okay, I'm going to go ahead and move on. We then spoke about derivative rules that you probably learned in early calculus classes, but then it might have been a couple years since you really needed to use them, and so it might be a little bit rusty. So we said if you want to take the derivative of something with respect to x, and that something is really the multiplication of two functions of x, then we have to be very careful about how we do this. So for example, I said that if f of x is equal to maybe x squared and g of x is equal to sine of x, And so, in other words, if I wanted to find the derivative with respect to x of x squared sine of x, I would need to use product rule here, because here is a function of x and here is a separate function of x, and they are multiplied together. So I do this by saying the first function times the derivative of the second plus the second function times the derivative of the first. Those are the words that I have memorized to remember this formula. Other people say it differently, and that's totally fine as long as you get the answer right. Okay, so for our example up here, that would mean that d dx of x squared sine of x would be the first, which would be x squared, times the derivative of the second. The derivative of sine of x is cosine of x, plus the second times the derivative of the first. So the derivative of x squared is just 2x. Okay? So that is our product rule. Then we talked about chain rule. We said that if we want to take the derivative with respect to x of a function of another function with respect to x, I need to be very careful here too. So an example that I used here, I think, was if f were, maybe you have an f of theta where you have sine of theta. And then theta in and of itself is a function of x. So maybe you have theta of x is 2x plus 2. You cannot take the derivative of sine of theta with respect to x. There's no x's there to take the derivative with respect to. You need to use chain rule. So here is our chain rule formula. Our chain rule says that I need to first take df dg. Sorry, let me rewrite that. If I want to find df dx, I need to first find the derivative of f with respect to g and multiply that by the derivative of g with respect to x. And I like to write it this way. I like to write the formula this way because it looks like a unit conversion in which the dg on the bottom cancels with the dg on top, and I'm left with df dx. So the way that I actually execute that for this equation here, or our example here, is that if I wanted to find df dx, or I wanted to take the derivative of f with respect to x, meaning I want to take d dx of sine of theta, it means that I need to find df dg first. So I need to do df d theta first and multiply it by d theta dx. And I can do these two things. I can take the derivative of sine of theta with respect to theta. That's just going to give me cosine of theta. And then the derivative of theta with respect to x is then just 2. Okay, so I get 2 cosine theta. Another way that you might have seen this done is by simply substituting in the theta expression up here and going ahead and saying, okay, this means that f of x is equal to sine of 2x plus 2. And in order to do the chain rule for this, you take the derivative of the outside, which is cosine of 2x plus 2, times the derivative of the inside, which is 2x. Okay, which is exactly the same as what we have down here. If you were to substitute in theta here, we'd have 2 cosine of 2x plus 2. Same exact answer. Oh, wait, sorry. I did the derivative here wrong. So just 2. Derivative of the inside is 2. Same thing. I understand why this one might make you a little bit more comfortable, but I want to encourage you to try to avoid doing this substitution here where you substitute in for theta to try to get rid of all the thetas, because there are later classes in which you will have to do a repeated chain rule. You're going to have to do chain rule once, and then you're going to have to do chain rule again, and you can keep going on and on and on. There are engineering problems in which you have to do many chain rules, and substituting back in every single time is just not going to be feasible, or as the math is not going to be as clean as doing the chain rule in this way. Okay, so I'm gonna try to avoid doing that substitution trick. Okay, last thing I want to talk about are free body diagrams. I really hope that you do in fact actually feel really confident about free body diagrams and you can draw a perfect free body diagram, but I have found through the years that sometimes there are some misunderstandings about what a really good free body diagram looks like, and we need to correct that now at the beginning of this term and not allow it to trip us up for the rest of this term. So for a 50 kilogram crate that rests on a horizontal surface for which the coefficient of kinetic friction is mu k equals 0.3, the crate is subjected to a 400 Newton towing force as shown. We want to draw this free body diagram. So free body diagram means I'm going to free the body from its environment. So I am not going to draw the ground. I want to free the body from the ground and replace the ground with the force or forces that the ground applies to the box. Okay, so for this box, we know that there are two different forces that the ground will apply to it. One is friction, and so we might draw friction like this. We might draw the force of friction equals mu k times n, where n is our normal force. So, spoiler, our normal force is also there, normal. So these are the two forces that we replace the ground with. These two forces represent that connection to the ground. So we no longer need to draw the ground. And if you do draw the ground, it's an incorrect free body diagram. Okay. We next need to fill in for the weight of the box. So we will add the fact that gravity points down, and the force due to gravity is the 50 kilograms mass times the acceleration due to gravity. And we talked really briefly in class about how if you're given mass in terms of kilograms, that is a metric unit. And so you need to use the metric version of g, the acceleration due to gravity, which is 9.81 meters per second squared. Okay, so kilograms goes with 9.81. However, we are also going to use English units as well in this class. And so if you are instead given the mass in pounds mass, then you will need to multiply it by g, where g is 32.2 feet per second squared. Okay. All right, so we have weight, we have normal, we have friction. Now we need to add back in that 400 newtons pulling force, and it goes this way, 400 newtons, and we absolutely need to have the angle that is working at denoted on our free body diagram so that we have any chance of getting our trig correct. All right. So that is a very, very common free body diagram. A box sitting on the ground with weight and maybe some external force. All right. Our last example is just another example. So here we have a forked rod is used to move the smooth 2-pound particle around the horizontal path in the shape of a limicon. We don't really need to worry about this expression. Here I am just asking you to draw the free body diagram of the particle. And so I'm going to draw the particle. I am not drawing any connection between this particle and the environment, but I'm going to replace those connections with the forces that they that they result in. Okay, so there are two key words in this problem. One is smooth. Smooth means that you can neglect friction. There's no friction between this particle and the path, or between the particle and the forked rod. The other key piece of information is the horizontal path. So the horizontal path basically means that you can consider this entire object as basically laying on a table in the XY plane where gravity is working into the page. So if gravity is working into the page, but really all we care about is acceleration in the X and Y direction, it means that when we draw our free body diagram in the XY plane, we do not need to have gravity, because gravity is essentially pointing into the page. And we're not considering that direction at this point in time. Okay, so that means there's really only two forces I need to draw here. I need to draw the force between the forked rod and the particle, and that is just going to be a normal force, so a force that is perpendicular to the forked rod. Okay, so this is a right angle here. And then we need to draw the normal force between the particle and the path. Okay, and the path is like this kind of radial function. Okay, and so our normal here is normal to the path and maybe path. And those are the only two forces on this free body diagram, because we are neglecting friction and we are considering this to be lying in the horizontal plane. And that's it. Okay, we will continue to reiterate the importance of free body diagrams, but for now, I hope you have a wonderful weekend, and I will see you in class next week.